Good morning, ma'am. My name is Pratyush and I am going to deliver a presentation on Turing machine in the context of theory of computation. These are my details. So let us proceed to our presentation. So the question arises first that what is a Turing machine? A Turing machine is a mathematical model of computation describing an abstract machine that manipulates symbols on a strip of tape according to a table of rules. Despite the model's simplicity, it is capable of implementing any computer algorithm. The machine operates on an infinite memory tape divided into discrete cells, each of which hold a single symbol drawn from a finite set of symbols called the alphabet of the machine. Proceeding, it has a head that at any point in the machine's operation is positioned over one of these cells and a state selected from a finite set of states. Based on the symbol and the machine's own present state, the machine writes a symbol into the same cell and moves the head one step to the left or to the right or halts the computation. The Turing machine is capable of processing any unrestricted grammar, which further implies that it is capable of robustly evaluating first order logic in an infinite number of ways. So, what are the contents of a Turing machine? So a Turing machine basically consists of a tape which is divided into cells one next to the other. The tape is assumed to be arbitrarily extendable to the left and to the right so that the Turing machine is always supplied with as much tape as its need for its computation. A head that can read and write symbols on the tape and move the tape left and right one and only one cell at a time. So now proceeding with the next topic, what is the formal definition of a Turing machine? A Turing machine can be formally defined as Tm, which is a set of Q, X, sigma, delta, Q naught, B and F, where we define each of these symbols. Q is a finite state of states, X is the tape alphabet, sigma is the set of input alphabets, delta is the transition function, Q naught is the initial state, B is the blank symbol and F is the final state. Before proceeding further, let us see the classes of automata. According to the theory of automata, there are four parts of the automata theory. This is number one is combinational logic, which is followed by number two finite state machine, which is followed by push down automaton, which is followed by a Turing machine. Now, to understand the application of Turing machine, let us look into a sample problem which demonstrates the application of this machine. So let us see the question. The question is construct a Turing machine for the language for that reads n number of A's, m number of B's and n into m number of C's where n is greater than equal to 0 and m is greater than equal to 0. Let us take a sample input A, B, B, C, C. So for this input the output will be yes, it is accepted by the Turing machine. Let us look at the solution for this problem. The given problem represents a kind of language where we use only three symbols, that is A, B and C. Language has n number of A's followed by m number of B's and then n into m number of C's. This is the design for the given problem. Now let us see the working procedure in the next slide to understand the design which has been given here. So step 1, we first replace the leftmost A by blank and then traverse to replace leftmost B by $sign and rightmost C by blank. Repeat this step from state Q1 till there is no more B left. Now we proceed to step 2. After replacing all the B's by delta by dollar, we have also replaced M rightmost C's with blanks and then we will traverse back to leftmost A and replace all dollar by B's. After this step, if check the string, it is now reduced to a to the power n minus 1, b to the power m and c to the power nm minus m form. At step 3, repeat from step 1 till all a's are not made blank. but after all C's are made blank, we encounter a blank B at state Q1, which we keep as it is and go to the leftmost blank. Step 4. So after all A's are made blank and if the string belongs to language L, then 0 C's must be left, which we check at state Q0 and Q6, as only B's will be left, and after which if blank is found, then all C's must have been replaced by blank, as we were making C's blank from rightmost end of the string. And the final step is, so if we get a blank symbol at state Q6, the string is accepted at final state Q7. Also, if the string was empty, then it will be also be accepted as blank symbol input at state Q0. Then it will got to go to state Q7 and gets accepted. So the conclusion of my presentation is that the Turing machine is the most comprehensive, deep, and accessible model of computation, and its associated theories allow many ideas involving complexity to be profitably discussed. Lastly, as an additional note, universal Turing machine can be used to simulate all type of other Turing machines. Thank you.